Well, so let us recall back from the previous lecture number 9, where we started the state of stresses, establishing equations for the stresses for 2D and then subsequently for the 3D metal forming processes. So this lecture number 10 will continue from the previous one, and let us recall where we considered the three-dimensional set of axis stresses and the Morse circle diagram we were deriving. So if you recall the particular this equation number the figure number 5, the Morse circle, this where corresponding to the equations of the 3 circle that we last time derived, and if we establish for the normal stress and normal shear stress for the 3-dimensional case, so we get the corresponding those 3 equations, and here is the Morse circle is plotted on the S and Sn axes. So one can see here that this sigma 1 that corresponds to the first principal axis, sigma 2 and sigma 3 corresponds to the and you can see here the C1, C2 and C3, the corresponding sigma 1, sigma 2, sigma 3 that cuts corresponding circles, one center having O1, center having O2 and center having O3. One can see here that and the corresponding locations. So if you recall the equations where the L, M, N, the direction cosines and all that was established, and that gives the axis the circle. So these equations particularly here, if you see m square sigma 2 minus sigma 3 and then sigma 2 minus sigma 1 plus sigma 3 minus sigma 1 divided by 2 square and then under root the whole thing, this one. So that gives the equation, and similarly the second part respectively. So when sigma 2 lies between the value sigma 1 and sigma 2, as one can see from the figure Morse circle, the equation number 11 gives, one can have the Sn minus sigma 2 plus sigma 3 by 2 whole raised to the power plus the shear part of the total stress square. It should be always greater than sigma 2 minus r equal to sigma 2 minus sigma 3 by 2 and the whole square, in case the sigma 2 is greater than sigma 2 and sigma 1. Since L square, that is the times square, is greater than or equal to 0 always, and therefore sigma 1 minus sigma 2 and multiplication with sigma minus sigma 3, it must always be either greater than or equal to 0. Similarly, the equation number 12 which was derived earlier, it gives similar equation as equation number 14 for the between 3 and sigma 1 and sigma 1, and similarly for one can see that sigma 2, since sigma 2 minus sigma 3 is greater than 0 and sigma 2 minus sigma 1 is less than 0. So, the equation number 13 can be used for calculating this way, that is Sn minus sigma 1 plus sigma 2 by 2 whole raised to the power square plus the S shear component of square, it must always be equal to sigma 1 minus sigma 2 by 2 whole square. So, since n square, that is the third component of the total stress, the cosine is always greater than or equal to 0 and sigma 3 sigma 1 multiplied with sigma 3 minus sigma 2 is always greater than or equal to 0. So, these equations 14 and 15 as well as 16 with the equality sign, which is that represents a family of the circle with the center at sigma 2 plus sigma 3 by 2 and 0, sigma 3 plus sigma 1 by 2 and 0 and sigma 1 plus sigma 2 by 2 and 0. So, these are the centers of the, if you recall back the equation number, the Morse circle equation, the diagram, and these have got radius as sigma 2 minus sigma 1 by 2, sigma 1 minus sigma 3 by 2 and sigma 1 minus sigma 1 minus sigma 2 by 2 respectively. So, these circles has been shown in equation number 5 and have been there. So, now let us assume this particular plot, the figure number 8, where let us assume a coordinate plane which ABC, which is equally inclined with all the 3 axes x, y, z. So, in that case let us establish what is Divoteric stress. So, Divoteric stress, as I told you, the total stress consists of two components, Divoteric stress and hydrostatic stress. And if we look into this particular figure number 6, where the plane ABC and the stress, main stress, the total stress direction has got direction cosine as L, M and N of the ON direction. This case the normal stress, which is capital SN, it was already calculated earlier. So, it corresponds to Sn, and that is L square sigma z plus m square sigma y plus n square sigma z plus 2 times of ln sigma xy plus mn sigma yz plus nl sigma z zx. When OA and OB and OCs, like in the previous figure 8, are all equal, in that case the direction cosines are equal, and that is equal to 1 by root 3, and since alpha, beta and gamma the plane is equally inclined with the x, y, z axis, so alpha, beta, gamma is equal, and then in that case L, M and all also equal, and therefore L square plus M square plus N square also sum of these 3 squares of the direction cosines is also equal to 1. And if x, y, z is taken along the principal axis direction, then one can have these as this principal stresses as sigma 1, sigma 2 and sigma 3, and then in that case the total normal stress can be written as L square sigma 1 plus M square sigma 2 plus N square sigma 3, and which is nothing but 1 by third of the sigma 1 plus sigma 2 plus sigma 3. And since sigma z sigma x is equal to sigma 1 and sigma xy is equal to sigma yz, and that is also equal to sigma xz, and these are all 0 and so on. So, as shown, the invariant 1, the first invariant which was calculated earlier, that was the summation of all the 3 principal stresses, sigma 1, sigma 2 and sigma 3. Therefore, one can write down this total normal stress, total stress in terms of the invariant 1, which is equal to 1 by 3rd I1, and similarly the mean stress, which we now say it as a hydrostatic stress, sigma m, and then it can be defined as 1 by 3rd of sigma 1 plus sigma 2 plus sigma 3, and that is nothing but 1 by 3rd of your invariant 1. So, the sigma m becomes a direct function of I1 and can be evaluated as 1 by 3rd sigma x plus sigma y plus sigma z, or simply 1 by 3rd sigma x star plus sigma y star plus sigma z if the axis is different. Since the invariants are independent of the direction of the axis, and therefore the mean also would be invariant and will remain the same for all possible orientation of the axis, and therefore it resembles the spherical nature of hydrostatic. Say in the hydrostatic fluid the pressure is all around same, so it resembles the spherical stresses which acts equally in all the direction as the hydrostatic stress or pressure. So, consider a tensile test where we have a specimen which is subjected to a uniaxial stress sigma, and secondly there is the stress sigma is supposed to have is supported by the hydrostatic pressure P all around. So, the element in the former case will be subjected to a stress sigma 0 0, because second and third component is 0, because in all the stresses in the hydrostatic it is same. So, in that case one can see that the sigma 1 minus P or minus P are so the experimental result shows that the stress strain in both the case remain practically the same even when very large hydrostatic pressure is applied. Similar results have also been observed in position when you apply the compressive stresses and as well as the torsion test. So, these results indicate that the yield and flow of most materials are nearly independent of the hydrostatic stress or pressure, and hydrostatic pressure namely causes and therefore causes an elastic change in volume which is recoverable on removal of the stress, and therefore from plastic point of view it is inconvenient to split the stress tensor into two. It is better to convenient the total stress into two component, one as the spherical stress tensor and second as your Divoteric stress tensor, and therefore here is the concept where the Divoteric stress is introduced along with the spherical, and therefore one can write down the spherical stress tensor, that is if it is represented by Pij, then it can be said that it is sigma m and chronicle delta Ij. So, this is a spherical component in this way, where sigma m is the mean stress and delta ij is the canonical delta as explained earlier, and therefore the stress Divoteric tensor, that is we would be writing as the prime for the Divoteric part of stress. So the sigma prime ij, it can be then obtained as sigma prime ij is equal to sigma ij minus pij, and therefore another way one can write down as sigma prime ij is equal to sigma ij minus sigma m canonical delta ij, and therefore the whole set of equation as we call it as the equation number 14 can be then written as like sigma prime xx, sigma prime yy, sigma prime zz, sigma prime xy, sigma prime yz, and sigma prime zx. So this can be extended further, equation number 40. So for an example, sigma prime xx can be expanded as sigma xx minus sigma m, and therefore it can further be, if the value of sigma m is introduced here, then it can be written as sigma 11 minus 1 by third and the summation of the sigma xx plus sigma yy plus sigma z, and therefore it can be simply written as 1 by 3 in bracket twice sigma xx minus sigma yy minus sigma zz, and likewise one can write down all these three set of equations, and this, let us call it as the equation number 41. So these stresses at point P, if it is shown in xy coordinate system, so as discussed previously, and so we have now x direction, we have now y direction. In, let us take this figure number 9. So we have now these three directions, and the point O is the origin of x, y, z, and O dash is the point P, where P is the point, and then one can have the hydrostatic stress representation here. So this is what the direction n is said, and the second axis which one can have the x prime, y prime, and z prime to represent it, the hydrostatic are mean stress axis, and the second one is the x prime, y prime, z prime as the Divoteric stress axis. So both are imposed here, one can see here, and one can see the components accordingly. So one can see here, for an example, sigma yy prime, which is equal to sigma yy minus sigma m, and therefore O prime is nothing but root 3 sigma m, and similarly OP it is nothing but sigma under root sigma xx prime plus sigma yy prime plus sigma zz prime, and therefore one can see the significance of the two stresses, hydrostatic or mean stress as well as the Divoteric stress, and at a point. So these stresses at a point with both Divoteric and hydrostatic part. So one can see here that the sigma prime, zz, yy, and xy, etc., all are called a Divoteric stress. The definition of Divoteric stress, therefore it implies that all the stresses should be considered with reference to a false zero, and should be measured not in absolute term, but it should be above and below the mean stress. Thus we obtain a new set of stress coordinates with mean stress as 0, and considered the coordinate axis in the previous figure, where figure number 9. So, here OP represents the resultant stress of the state of the stresses sigma x, xx, yy and zz, whereas O prime is the mean stress state, and O prime P as the resultant Divoteric stress with components as sigma prime xx, sigma prime yy and sigma prime zz. As previously, the mean stress has negligible influence of the on the yielding and flow of a material. Therefore, for analyzing the behavior of the material undergoing plastic deformation, it is better to consider the Divoteric stress system, which is which can be obtained by substituting the spherical state of the stresses from the actual state, and the invariants for the stress can therefore be found out by just replacing capital S, the total stress, by that is the capital S prime, that is the Divoteric, plus 1/3 of the invariants, first invariants in the previous equation number 28, and therefore one can find out this particular set of equation number 42, where S prime cube I square plus 3I2 by 3 and S prime minus under bracket 2 I cube plus 9 I1 I2 plus 27 I3 divided by 27, and that this 2 makes 0, and therefore one see here in equation number 42 that the three variants, all the three variants comes into invariants comes into, and this equation can now be further written in the tensorial in this form, not tensorial but in this format, that is the S prime cube minus if you simplify the equation number 42, so minus I1 prime and S prime square minus I2 prime S prime minus I3 prime, and it is equal to 0, where the I1, I2 and I3 primes are with Divoteric part. So, the first Divoteric part is 0, and second Divoteric part is the I1 prime plus 3I2 divided by 3, and similarly the I3 prime is equal to 2I1 cube plus 9I1 I2 plus 27 I3 divided by 27. So, in the direct stress form, this component the invariants can be obtained again, like I1 prime is 0 and I2 prime is 1/6 of the sigma 11 minus sigma yy whole square plus sigma yy minus sigma zz whole square plus sigma zz minus sigma zx square plus 6 times of your sigma xy square plus sigma yz square plus sigma zx square. So, this equation 44, it is the another form, and therefore one can further expand the I3 prime, that the Divoteric part, the third invariant of the Divoteric part, and it can be written as the long equation which is here given in this form 1/27, and under whole set of this, that means it has a 1, 2, 3, 4 and 5 long components, and therefore this set of invariant, that is the Divoteric part of the invariant under such situation, can be now represented in the tensorial form as I1 prime as 0, I2 prime as as sigma xx square plus sigma y sigma xy square plus sigma yz square plus sigma zx square minus sigma xx prime sigma yy prime plus sigma yy prime sigma zx prime plus sigma zx prime and sigma xz prime. And similarly the third invariant Divoteric part can now be, this previous long equation can now be written as very simple form where it is 1, 2, 3 and 5 components. So this particular equation number 43 can also be obtained by making approximate substitutions in the previous equation 28. The roots of the equation 43 are the Divoteric principal stress sigma 1 prime, sigma 2 prime and sigma 3 prime, and the invariants in the term of these stresses can be written as, therefore I1 prime is equal to 0, I2 prime is equal to half of sigma 1 prime square plus sigma 2 prime square sigma 3 prime square. So the invariant 2 Divoteric part is now represented into the direct stress Divoteric part of the stress, and similarly I3 prime. So this 40 this is 40 equation number 46. So in then tensorial form it becomes much more compact. So I1 prime is 0, I2 prime is 1 by 2, sigma ij prime, sigma ij prime, and I3 prime is simply 1 by 3 sigma ij prime, sigma ij prime, jk, sigma jk prime and sigma k ki prime, and where the I, j and k varies from 1 to 3. So 3 9s are 27 and therefore it is okay. So with this foundation of Divoteric, hydrostatic and the Morse circle and the representation of the stresses at a point in the format of Morse circle in 3D space, we can now make use of the equilibrium equations. So in general the state of stress in a body varies from point to point. One of the important set of equations used in the analytical problems of metal forming deals with conditions that satisfy the stress component when they vary from point to point. So these equations of the stress equilibrium can be now derived using the element of the stresses on a body, and one can then write down a free body diagram. For suppose now let us take this figure number say 10, where we have a free body of a block, and one can see the x, y, z axis is taken here, and one can now write down the equilibriums of the different element of this body. So one can see for in here the sigma yz, sigma yx, sigma zx, and these can be written as, so the across the plane the different stresses that are acting one can write down now, and if it is multiplied by the cross sectional area, and so one can write down these 1, 2, 3, 4, 5, 6 major component of the equations. So one can see the rate of change of the stress component with increase in x and y and z, which is kept constant, and therefore we get the this rate of change of the stresses with directions x and y and z. Similarly, the rate of change in the stress component for y and z can be written as in this form, and for the z component like deva sigma xx with deva z, then sigma xy, sigma xz with component z respectively, it can be written. So if the body force component per unit volumes are considered, and that is in the direction of x and y z. So if these body forces are taken as B for body, so Bx, By, Bz, so the equilibrium equation can now be with respect to the previous figure 10, one can write down the equilibrium equation in direction, and therefore the total equation becomes this one. So one can see here from the, if with respect to figure number 10, that this is the stress and then yz on the yz plane, and therefore the area of this. Similarly, the minus of zx and then yz, so the normal component. So set 1, 2, 3, 4, 5, 6, all these sets are, when it is added, all these things must be 0, and therefore this equation comes out to be 0, and therefore it can further be written in this format, where the del sigma zx by del x and then delta x, delta y, delta z plus del sigma yz divided by del y and del x, del y, del z plus deva sigma zx and other component, and then the last one where the body forces Bx, delta x, delta y and delta z is considered in the x direction, or simply it can be written as this equation. So corresponding to the total stress in the x, the body forces in x direction. Similarly, the equilibrium in y and z direction gives these two equations. So these three set of equations, if it is represented in the tensorial form, it can be written as del sigma ij divided by del deva xi, where xi is the direction x, y and z. So deva with respect to the direction, so that sum is 0. When the body force are taken 0, that means deva sigma ij divided by deva xi plus rho, that is the density, and fi and bi, it has to be 0. When the body force per unit mass are considered as your, so this equation where fi and p's are p is your say mass density. So the force equilibrium equation, if you for the moment equilibrium, then we can consider the moment of the force about x, y and z axis must vanish individually, therefore. So taking moment about an axis which is parallel to the z axis and passing through the center of the point of the cube, if you the earlier equation number 10. So we can take this the force equilibrium, where you can see in this figure where the volume V and the small area, if it is taken on the volume which is equal to ds, and the normal to the area is Nj, and Fi is the force acting on that small area, and therefore if we take the moment equilibrium equation, we can write down the moment equilibrium equation like here. So if we cancel delta x, delta y, delta z by 2 on both sides of this particular equation, left side and right hand side, so this gives 2 sigma yz plus deva sigma yz by y and delta y, which is equal to twice of the sigma xy plus deva xy by x deva x. So this in this particular limit where the delta x, delta y and delta z tend to be 0, very small, so therefore sigma xy and sigma yz x is similar. So similarly for the other two directions, like can be kept as sigma xy, which is equal to sigma y z is equal to sigma xz. So if we consider the equation the figure 11, where the having volume V and the surface area, so we can substitute the surface area which is acting on because of the force F, and then one can find out the body force per unit volume if it is taken as say GI body force, and the acceleration field vector if it is taken as AI, then the equilibrium equation of the force can be represented as integral over this particular surface Fi ds plus over the volume, which is the body force and its area, that is dV, and minus over the volume the density, the acceleration and the dV. These three sum must be 0. So this equation number 50, where this rho represents the mass density. So let us consider an arc in this figure number 12 AB on the material surface, which is normal, which is outside normalized on the xy plane with unit vector n prime, which is normal to AB, and having components say ANX and y axis have the direction, and the shear stresses on this, say it is sigma zx, sigma yy and sigma xz. Sigma yz, as it is shown here, if you look into the this particular this figure, so of any surface where this particular surface, so fx, fy and total resultant is capital F along the directions, along the unit directions. So xy if it is considered, so this equilibrium of this particular surface ds, small surface ds, so one can write down this equilibrium equation in this format. So the element for the particular element ABC, one can write it in this form, which is fx ds is equal to sigma xx and z ds, which is normal, plus sigma xy ny ds, and therefore the force x component force can be written as here in this two form, and similarly the vertical equilibrium of the equation can be written as Fy is equal to sigma y and z plus sigma yy and y, and this equation number 51 and 52, and it can be generalized in 3 dimension as well as, and it can be then in tensorial form it can be written as Fi is equal to sigma ij and nj. So this is the tensorial form, and this can be further extended in the 3 format, that is Fi when it is x, y and z. So for an example, fx can be written as then sigma xx nx plus sigma xy ny plus sigma xz nz likewise. So if you substitute the fi value as sigma ij nj, the force equilibrium equation which was earlier given in equation number 50, it can be written as this one. So integration over the surface, that is component of the stress sigma ij, plus over the volume including the body force, and minus of the density, that is the acceleration component, mass component over the volume. So this 3 summation, it must be equal to 0, and therefore the surface integral capital S can be now further be converted into the volume integral by using the divergence equation, and therefore the surface equation can be further converted into the volume integral, which is using dou ui divided by dou xz dv, and therefore the equilibrium of the force one can see here, where ui is the corresponding vector of the u, which is an elemental area ds of the closed volume V, and nj are the components of the unit vector directed along the outside normal to the ds, and therefore this equation can be written here, this equation number 57. And for say and very small, if this area ds becomes very small, that is infinitesimally small volume, and then it can be shown that this equation is the equation number 57 can be represented at this here, when it is the volume is very small, and when the body force and the accelerations or the inertia forces are also negligible, considered to be negligible. So therefore this equation number 58, which is the equilibrium equation, can be reduced to a very simple form in the derived stress equilibrium equation, and this forms the basis for equilibrium equation. And with this equilibrium equation we can correlate there to further